Hello, everyone. Welcome back. Today, we want to talk more about limits, and specifically, we want to talk about some of the rules of limits. So, our goals, well, first, we'll start off talking about the limits of a polynomial function. Then we'll look at some actual limit laws, and also you can call to what those are, how to use them. Also, something called a squeeze theorem to evaluate limits, and look at some other concepts as well. So, first, let's talk about limits of polynomials. Remember what a polynomial is. Go over here at the left. Polynomial is basically one of the kind of more or less the kind of nicest function you can have. Okay, it's a function where it's usually some function. Of course, you can actually have polynomials of more than one variable. Here, we're just looking at one variable at a time, just x. And so you have a function of x, and um, your powers, your exponents, are always whole numbers. Remember, whole numbers like 0, 1, 2, 3, and so forth. So no fractions, no negative numbers, no decimals, anything like that. Okay. And then the ANs, numbers out in front, are real numbers. Those are just your coefficients. So basically, we also tend to write them what's called descending order, with what's called the degree, the highest power first, and then all the way down to if there's a constant. Okay. That's a polynomial. Those are nice functions. And they're nice functions because the domain is all real numbers. You can plug in any number you want, and they don't have asymptotes or anything bizarre going on, no holes, no asymptotes, nothing like that. They're nice functions to work with. Now, as far as the limit of polynomial, that makes the limits very easy. Talking about the limit of a polynomial is to go to some specific number, we just plug that number into the polynomial. That's why this is really nice. And because of that, also your left and right hand limits are the same. Okay, because once again, these are really nice functions. Let's just look at a couple of quick examples over here and recall what polynomials are. So some examples. Number one, what about just the limit as, say, x goes to 3 of the number 5? Actually, a constant is a polynomial because I think of that as being 5 times x to the 0. But once again, if you think about it, of course, if you don't realize that's a polynomial, if you think about it, 5 is a horizontal flat line where every number is 5. So when x goes to 3, actually, no matter what x goes to, 5 is always just 5. Okay. Other basic functions like a linear function. Let's say I have the limit of x goes to -2 of 3x plus 1, for example. Well, once again, that's a polynomial. Okay. Our power here for x is a 1. Our coefficients or numbers in front are real numbers. So basically, we just plug in -2. And that's going to be -6 plus 1 is -5. And of course, that's true for also the left and right limits both equal the same thing. Let's do another quick one. Okay. Even something a little more complex. Let's say x, and we can also do limit to 0. X goes to 0 of, let's say, 2x cubed plus x. Not terribly exciting. Once again, the same thing. Just plug in 0 for x, plug in your whatever you want your x to be. Whereas this case, that's just 0. Okay, so polynomials are nice in that way. So they're one of the best functions to work with because they're simple. They don't have any really surprises. Now, next thing I want to talk about, let's talk about the limits and the domain of a function. So some functions, some are only defined for specific domains, either because maybe something doesn't exist, or maybe some output doesn't exist for some number, or maybe because you have some kind of artificial limit on it. Um, so let's look at this over here. It's limits and the domain of a function. Okay. So for a limit to exist, we must approach it within the domain of the function. So I'll give you an example here. So let's come back over here to the left and we'll explain this one a bit more. I'll just say limits, kind of how this limits and the domain. Okay, so I'll give you an example. If we take the limit of x as x goes to 0 from the right of the square root of x, and also this is a good example. This is not a polynomial, okay? So we can't just take it wherever we want, all right? Of course, remember this is a square root, so let's actually go to Desmos. So Remember DSOS.com. Let's go to graphing. Now, if I'm also going to graph a squared function, there is, if you go down here to the functions, there is a square root down here, right here. Actually, the easy way to do a square root is just type in SQRT, SQRT, and then X. Of course, that's our graph. Now, if you notice, our domain, it only starts at 0 because if you plug in anything less than 0, anything negative, it makes it imaginary. So that's not in our domain. Okay. So I can approach 0 from the left, or sorry, from the right, from above. I can't approach it from the left because it's outside the domain. So let's go back to that example. Okay. So this from the right is just 0 as we saw in the graph. Okay. But call that A, but B, limit as x goes to 0 from the left of the square root of x does not exist, at least not in real numbers. Okay. Now, so that's a good example of something like that. And I say that over here, since negative values x make the function imaginary. What if we even do another kind of example? Let's say we do another example. Should we call this number 1? Let's call this number 2. I think I can squeeze it in right here. Let's see, what should I want to do? Well, let's just do our f of x is equal to simply just x squared. But let's say our domain is just going to be from 0 to 2. Okay. So you know what that function looks like. So this is going to look something kind of like this. All right. So here, this function starts at 0, 0 and ends at 0, or sorry, not 0, but 2, 4. So our domain goes from 0 to 2, so it goes from those 2 points. Okay. Now, obviously, the function x squared by itself is a polynomial. It goes from all real numbers. But in this case, we're just saying we're making for some reason, our domain is constricted right here. So in a similar way, let's go down to the next page. I'll just say, so if you take the limit, for example, as x goes to 2 from the left, from below, that's going to be of x squared is going to be 4. Okay, that's fine. But if we try to do the same, or a limit as x goes to 2 from the right of x squared, once again, based on this domain of this function, let me actually just say, actually change it. We call this f of x to make sure I'm not talking about x squared in general, this specific f of x with this specific domain, then that, imagine here, since that doesn't exist to the right of 2, this one does not exist. And so if you remember in both cases, in number 1 and number 2, what that means is that the limits, I was going to say, so just the limit as x goes to 2, the total limit of f of x does not exist. Remember, for it to exist, the total limit has to be true from both sides. It does not exist. And that was actually true of this one up here, of square root of x as well. So you can approach square root of x from the right, just can't approach from the left, so the limit at 0 does not exist. Okay. Next idea is something called a squeeze theorem. Let's talk about that below. Oops, what did I just do? Hang on. Ooh. Yeah, that was strange. This is one that can be useful sometimes. All right, so the squeeze theorem, in mathematical terms, is say you have 3 functions. Okay, and we're looking close to some point B. Okay, so let's, as we talk about this, go and start to draw it. So actually, we don't really need, well, yeah, I guess we can't go ahead and do that. All right, so if we need axes, but yeah, I'll go and draw axes on here. Let's say we're interested in some point B. Okay, so max value B. All right, let's say we have 3 functions, and this is true. So f of x, at least close to B, f of x is always less than or equal to g of x, which itself is always less than or equal to h of x. Okay, so let's draw that. So let's first off draw the one in the middle. So let's say this is g of x. And let's say maybe they all kind of converge right down here, b. And this is h of x above. And then below, we have f of x. Okay. Now, at this point right here at b, what this says is that basically, let's also say this y value right here is L. Let's call it L. Then what the squeeze theorem says is then that, as you can see, the limit as x goes to b of h of x is equal to L. Okay. And also the limit as x goes to b of the lower function f of x is also equal to L. L. Same point. Okay. Then since, and also I forgot to write this. So h of x, let me write this. So f of x, I'm going to write everything is less than or equal to g of x is less than or equal to h of x. I forgot to put that up here, but I also want to make sure it's here on my graph as well. Okay. So what this implies is since g of x is always between fx and h of x in this area, close to b, around b, if the limits of both of these are L, then that implies, that tells me without even checking that the limit as x goes to b of g of x also has to be equal to L. I keep writing 4. Okay. So let's look at an example on Desmos, kind of show how that works. So let's go back to Desmos. Let me just turn this one off. We always turn on or off using this, toggling that right there. Let's do a couple of graphs. Let's do some graphs we're familiar with. Y equals x squared. Okay. Now, that will be our g of x. Okay. Let's do also y equals, now space there, h of x. Let's do 1 equals 0.5 x squared. Oops, 0.5 x squared. Okay. And let's do one more. Let's do y equals negative x squared. Okay, so let's zoom in on this. Of course, these colors are kind of similar, but so let's say this top function, this is our h of x. Bottom function is our f of x, and this middle function is our g of x. Now, if we trace out f of x at 0, for example, it goes to 0. Okay. And once again, this is clearly, I think clearly see this is true. The h of x is greater than g of x is greater than f of x. Okay. If I trace out h of x in the same way at 0, it goes to 0. So what that means is that since this green line is always between these other two, this kind of purple line and blue line, which are kind of similar colors, what Desmos shows, then always basically, since both those functions, what I call the sandwich theorem, both the top and bottom functions go to 0 at 0. That means my green line, my 0.5 x squared, also has to go to 0 at 0. I don't have to, can trace out, but I don't have to. As you see, if I trace it, it's the same thing. It has to because it's always in between. That's why it's called the squeeze theorem. Or something that's like the sandwich theorem, is you're right in between those. Okay. And that's kind of a useful thing sometimes to have. All right. Next, let's talk about some laws of limits. I don't know what that was. A few quirks with this writing pad. Okay. Let's stop at the laws of limits. All right, so for some, we have laws for certain limits. Let's take a look at these over here. All right, so this says assume, in this case, we're talking about going to A instead of going to B. So, but you can think of it however you want to, it doesn't matter. So we say the limit as x goes to a of f of x and the limit as x goes to a of g of x both exist. And that means they're both true from both sides. And these following properties hold, where c is some real number and n is greater than equal is an integer. Okay, so these are some useful laws of limits. So let's take a look at, we're not necessarily doing an example of each one, but kind of talk about each one a bit. All right, the first one says a sum. So I have a sum of two functions. And notice I didn't say I have to say anything about these functions. They could be polynomials, it could be any kind of functions. As long as those limits exist at a, then I can essentially, it's not quite, would call it distributing, but it's kind of like that. Okay, I can break them up and do each limit separately. So the limit of the sum is what's called the sum of the limits. Also, I have a difference the same way. The limit of the difference, it becomes the difference of the limits. And of course, being a difference subtraction, make sure I keep the order right. It's got to be the limit of f minus the limit of g. Okay. I have a constant multiple in front of my function. I can essentially move that out front. Okay. So it becomes c times that. Okay. And also, those you take in calculus, you learn these. Since what's called a derivative is also a limit. These rules also work for derivatives. Okay. Also, a product, the limit of the products, f times g, is also, I can then essentially take the limit inside both and multiply those limits together. Also, for a quotient, a fraction, the same way, provided that my function doesn't go, provided this bottom function doesn't go to 0 at x equals a. Now, if that's the case, you may have to do some extra work. It may not necessarily be the end story. You may have to do some work to kind of rewrite a different form to make it able to work with. We'll see some examples like that here in a moment. Okay. Power. So if you have limit of f of x, some power n, we said n had to be an integer. Then basically I can essentially take the power of that limit. And then also the same thing here. If my limit is 1 over, a root is a root, which is the same thing as 1 over n power, same kind of thing. And once again, provided f of x is greater than 0, it's not going to be imaginary or anything like that. Okay. So let's practice with a few of those. Like I said, I'm not gonna do one of each, but just kind of give you some ideas. So number one, some examples. Okay, I don't know what I'm doing that's causing that. Okay, so number one, let's say I want to do the limit as x goes to 5 of 3 times x cubed. Okay. All right, well, one thing we learned is we can actually use this property here. Okay, so I have a constant of 3 in front of x cubed. So what it says, I can essentially kind of take the limit inside, move the constant out front. That's going to be 3 times the limit as x goes to 5 of x cubed. And x cubed is just a polynomial. And so what this is going to be is 3 times, just plug in 5 cubed. So 5 cubed is 125. So 3 times 125. And that's going to be 375. Okay. Now, of course, the case is a polynomial was a nice function. If it isn't, you may have to be careful about that. But still, in this case, that's what this limit law says. I use that one. Okay. We did one like this a minute ago. I'll say the limit as x goes to -1 of, let's say, 3x plus 1. Okay. Now, this also itself is a polynomial, so we know we just simply plug in -1 for that. We can also use the rules if you want. It's not, I wouldn't call it distributing. It's like distributing. Make this limit as x goes to -1 of 3x plus the limit as x goes to -1 of 1. And then actually, I can also use that same rule here, the rule of the constants. I can make this as 3 times the limit as x goes to -1 of x. And then plus the limit as x goes to -1 of 1. Okay. Now we know it's going to be, of course, the limit as x goes to -1 of x is just going to be 3 times -1 Of course, the limit as x goes to -1, more like a -1, which is going to be +1. And so that's going to be 3. Well, -3 plus 1 is going to be -2. Okay, so you get the idea. Like I said, we're not going to do all those. We'll work on a couple of those here in a moment, again, as an example. All right. Now, let's take a look at some that are a little harder to, maybe a little harder to figure out at first. Let's actually take a look at a rational function. So number 3. Let's say we want to do, first off, as a limit. Limit as x goes to, first, let me actually write out what I want to do. Is x squared minus 4. Where you x plus 2. Let's go to -2. Okay. Now, this will also show an idea how this works and also some things that can actually happen. All right. So let's also use this rule here for a quotient. Okay, let's approach that. So let's take the limit of both numerator and denominator. So this is going to be the limit as x goes to -2 of x squared minus 4. And then this is over the limit as x goes to -2 over x plus 2. Now, you can also break these up if you want, using the sum rule. We don't have to do that. But basically, we just try and plug in what we have. Okay, let's plug in -2s. Actually, both of these are polynomials, the top and bottom, so we plug those in, -2 in. -2 squared minus 4 over -2 plus 2. And you probably see what's going to happen. This is going to be 4 minus 4 over 0. This is going to be 0 over 0. Okay, now, technically, this is undefined. And also notice we didn't do anything wrong. We used the rules, except here we found out that basically, this rule is true as long as the limit of the denominator doesn't go to 0. And that's what happened here. It becomes 0 as we go to this -2. Okay. Now, there's another way we can figure this out, another thing we can do. And what we're going to do then is actually another way to approach this. Well, first off, what we can do is let's actually graph it. So let's go back to Desmos. So one of your first tools is going to be to graph it, get an idea of what it should look like, and then you kind of go from there. That can give you some hints sometimes, some ideas. So let's go back here and actually just erase all of these, delete them all. Okay. So what a graph is, and also if I want to graph, I want to mention this, if I want to graph something involving a fraction, make sure you put your numerator in parentheses. If you don't, if I try to divide something, it just divides the 4 by that if I don't put parentheses around it. So put parentheses around everything. And divided by x plus 2. Oops, I probably need to zoom out. Yeah, there we go. Oh, that's not right. X minus 4. There we go. Okay, good. If you notice, that's just a straight line. Now, why is it a straight line? Well, what that means is basically, in this case, you might have noticed this already, something's going to factor. So let's go back and take a look at the original one. Let's try and factor this. So the limit as x goes to -2 of x squared minus 4 over x plus 2. We factor that. Also, one thing I want to mention is that x also still cannot be -2. That's what we didn't mention before, but you can see that now. So the limit as x goes to -2. If we factor that, the difference of squares, that's going to be x minus 2, x plus 2 over x plus 2. Those will cancel out, and we're going to have this to be the same as the limit as x goes to -2 of x minus 2. But we'll also have to remember that x cannot equal -2 because that will make the original function 0. Okay. So what you would have then is, we go back to Desmos for just a second. What you'd have at -2, let's zoom in some. At -2 right here, you'd have a hole in the graph. And see, in fact, you can see right there, it says undefined. Okay. There's actually a hole. It actually shows you a hole in the graph. It just doesn't show up very well. It's actually undefined right there. Okay. That's another nice thing Desmos does. It's actually undefined. Okay. So now we can just simply plug in our -2. This is a polynomial. And so this limit, well, it's going to be, if we plug in -2, it's -4. And if we go back to the graph, and if you graph this on your own, you see that basically is here. That's undefined right there. You can see the limit, the y value is approximately -4 above and below. The thing about our left and right limits at that point, they close in on -4. So that is our limit. Okay. Now, let's look at another couple like that. Actually, number 4. Let's look at one with a, this one may look strange, but let's do this. So limit is about to write an x. I'm used to writing x's, but this time it's going to be an h goes to 0 of this expression. So we're going to have this 5 plus h squared minus 25 over h. Okay. Now let's go and make a couple things clear. So obviously here, h cannot be 0. Okay. So if you try and take the limit written this way, try to do the same approach. Okay. Because basically this would also be a polynomial in h. If you try and plug that in, okay. They try and make that 0 or 0. So it's going to be 5 plus 0 squared minus 25 over 0. That would be 0 over 0. Okay, similar to the result we had before. Okay, as you can see, that's going to be a problem. So once again, let's actually go to Desmos first. Let's graph it. Let's kind of get an idea what it should look like. So I think I'll just turn this one off. And so we can type it in. I'm going to use x here instead of h, but it's the same idea. So 5 plus x squared minus 25. And once again, you need to go back and put parentheses in over the whole thing if you want to divide by x. And zoom out a bit. Once again, we get something a straight line. That tells you that there's things going on. Let's see it's 0 and may even show undefined. Yeah, it's 0, it's undefined. You can't see a little white circle there. It just doesn't show up that well. It's undefined. So why is that true? Well, let's actually, now we also get an idea what the limit should be. Okay. Looks like I'm approaching, as I approach 0 from the left, looks like it's approaching 10. As I approach 0 from the right, looks like it's also getting close to 10. It looks like my limit should be 10. Let's see if we can show that exactly. Okay, because you may need to be able to write that, give an exact answer, not just approximate answer. All right, so what we're going to do then, let's go back here, is let's actually multiply the top through, okay? I'll just call this another way. So the limit is h goes to 0. So I'm going to multiply this through. So remember, you can't distribute power. So what this is going to be 5 plus h times 5 plus h minus 25. Those are h's. You do better h's. Might look like b's to some people. Okay, over h. Now, when you do this, then this is also going to be, so I have the limit out here. Don't forget the limit part. H goes to 0. And so actually, if you FOIL this out, I'm going to go ahead and kind of cut the chase and go ahead and write all that out instead of showing all the steps. But remember how to FOIL. So it's going to be, outer one's going to be 25. Everything's a plus. That makes it nice. So also we have, both these are going to be the same. 5 times h plus 5 times h is 10h plus h squared minus 25. Of course, this is still over h. Okay, of course, the 25s cancel out. And so I have limit is h goes to 0 of 10h plus h squared over h. And probably the easiest thing to do here is just break this up into two fractions. So the limit is 10h over h plus h squared over h. And yeah, as we'll see, what happens nicely here is this gets a lot better to work with. So these h's cancel out. Here I have one h cancels out here. And so this is going to be equal to 10 plus h. And now we'll still have the limit of that. And I'm actually going to put parentheses around these to make sure it's clear. I'm taking the limit of the whole thing. So 10 plus h. And now, if I plug in, I can now plug in h for 0. This is just a polynomial h. If I plug in 0 for h, this is going to be 10 plus 0 is equal to 10, which is exactly what we thought it was. Okay, so we can solve from the graph what the limit was approximately, but here we're actually able to find the exact value. All right, let's do one more of those. And I guess this is number 5. Okay. Let's do this one. So once again, another limit using h as h goes to 0, okay, of square root of 100 plus h minus 10 over h, okay? Now, and once again, of course, h can't be equal to 0, okay? And once again, the same thing, if you try and do h, if you plug in h equals 0, then obviously this becomes 0 over 0. Okay, so once again, now this is one's good. Another way is going to be a bit different. And the one reason I'm showing you this because this is really kind of strange and something you may never thought of before. And find the exact answer. But also, once again, let's go ahead and graph it and see if we get an idea what it looks like on Desmos. As we'll see, it's not going to be as bad as it may look like. Okay, so I'm going to do a large numerator. So put parentheses and do square root, do SQRT. So 100 plus, I'm going to use x instead of h, minus 10. What was my parentheses divided by x? And if you notice, let's zoom in on that. Okay, so this number is approximately, actually just a constant, it's a flat line at 0.05. Okay, so now if you need an exact value, that's your limit right there. And once again, if we go right here, probably say undefined. Yeah, undefined right there, actually at 0. You can see from the left or the right, it's basically going to be 0.05. Now, to get an exact value, we're going to do something really strange. You may have done before rationalizing the denominator. Rationalizing is called rationalizing the numerator, which is, like I said, this is very odd, but this will actually work in this case. So I'm going to rationalize the numerator. Okay. What we're going to do is going to multiply the top and bottom, numerator and denominator, by, so we're going to take this expression, I'm going to change this middle sign. Here's minus, make that plus. So 100 plus h plus 10, okay? And once again, I made to be clear why I'm doing this. And some of you may have rationalized the denominator in a similar way, but you may have never rationalized the numerator. So this is going to be then, once again, this limit is h goes to 0. So the same numerator, 100 plus h minus 10. Now times the square root of 100 plus h plus 10. And then the denominator is going to be h times the square root of 100 plus h plus 10. Okay, and once again, be wondering why we're doing this. Well, rationalizing is a way of getting rid of a radical, getting rid of, in this case, a square root. So basically, actually, as we'll see, in doing this numerator, actually get rid of the square root. So hopefully, if you notice something, if you FOIL this out, you'll see this. But if you notice something, this is basically an example of difference of squares. So you have exactly the same thing, except we have a plus and a minus in the middle. But our terms are the same. So if we combine this, either FOIL it, or if you remember the shortcut, difference of squares, this is going to be the square root of 100 plus h squared minus 10 squared. Okay. Then that's going to be over. I'm just going to leave this. I'm not going to multiply this through yet. I'm just leave it as it is for now. The square root of 100 plus h plus 10. Okay. Now, remember, if you square something with a square root, basically cancel out the square roots as long as what's under here isn't negative. And so that's just going to be, it's going to our limit as h goes to 0, be 100 plus h minus, then of course 10 squared is 100, over, and the same denominator, the square root of 100 plus h minus, or plus 10 rather. Okay. Now what this is going to be, and one thing that's kind of annoying about this is having to do all the writing. Of course, our hundreds and negative 100 cancel out. Then we have h over h times square root of 100 plus h plus 10. And now, if you can see, the h's will cancel out. And I'm left with this as the limit is h goes to 0 over 1 over the square root of 100 plus h plus 10. And now if I plug in h, this is going to be 1 over square root of 100 plus 0 plus 10. Okay. And I think is what's going to happen. Of course, the square root of 100 plus 0 is the square root of 100, which is 10. That's going to be 1 over 10 plus 10, or 1 over 20, which is equal to 0.05. So as we saw from Desmos, we got exactly the same thing. Okay. 0.05. All right. Now, once again, that was said was a very weird example because rationalizing the numerator is not something you do very often, fortunately, because it's kind of a pain. But it's something is a technique you can have if you need to. Okay. Last thing I want to look at for today is let's look at piecewise function. Remember, a piecewise function is basically, as kind of the name says, a function made up in pieces. Okay. So let's look at let's call this our f of x. I'm going to have two pieces for my function. I'm going to have the square root of the first piece is going to be the square root of x minus 1 whenever x is greater than 1. And then I'm have a linear function x minus 1 whenever x is less than or equal to 1. Okay. So first, let's draw that. Let's use Desmos to help us out and get an idea what this looks like. Okay, of course, this is this is a linear function. Now, I don't really know if we can actually get a way to do linear functions in Desmos, unfortunately, or piecewise functions. There may be some way. But we can get an idea from this. First, let's kind of zoom out a bit. Okay. So the square root SQRT, x minus 1. And then the other one is x minus, so x minus 1 or x plus 1. X minus 1. Okay. All right. So what I said was that when x is greater than 1, then I have this square root function. When x is less than 1, I have this linear function. Okay. So let's graph that. So now we have an idea what this looks like. Okay. Let's go back to go back here. Okay. So right here, actually technically for this part right here, for this square root of x minus 1, okay, and this point right here is going to be 1, 0, okay. Actually, I have an open circle for the top part because if you notice it's not included in that part, right? Greater than 1. But here, I have this part, this linear function, which intersects right here at 0 and negative 1. But actually, it is included right here. So when x is 1, y is 0. So actually, it is included in this part. this looks like this. And also draw some arrows in case we want further in both directions. Okay. Now, let's take a quick limit. Now, in this case, they end up intersecting at the same spot. Okay, and actually intersect the same point. So what if I do the limit as x goes to 1 from the left of f of x? So the main part of this and kind of learning this is understanding what part you're looking at. Okay. Now, if I said the limit as x goes to -1 from the left, okay, which part am I on? Well, when x, the left of 1 is going to be when it's less than 1. So you're looking at this part, okay? And so we're coming in from the left to 1. And as you can see, as I get closer and closer, as x is closer and closer to 1, y is closer and closer to 0. That's the limit of that. So that's 0. Okay. I did the limit from the right. Okay, so in this case, I'm on this top part of the graph when x is bigger than 1. I'm on the right of 1. So I'm coming in this way. And also my limit is also 0. Okay, if we go back to Desmos, we can check down Desmos pretty easily. Okay, so if I'm on the green line, if I'm coming from above, from the right, as I get closer and closer to 1, y gets closer and closer to 0. And then from the left, going below, the left of x is closer and closer to 1 and closer also to 0. In this case, they both have the same limit. So if left and right side limits have the same limit, what I can say then is then the limit as the complete limit as x goes to 1, complete limit of f of x is equal to 0 since they're equal. Now, if I had some other function where it didn't meet up at this point, then these two probably wouldn't be equal, probably wouldn't be the same, and this total limit wouldn't exist. In this case, it does. Okay, just keep in mind, so with a piecewise function, so make sure wherever it is, point you're trying to find the limit, make sure you're using from either the left or the right, the correct part of the graph, the correct piece. Okay, so quickly let's review what we've talked about in this video. Okay, so we talked about polynomials and nice functions. So basically to find the limit of any polynomial, any number, just plug in the number. Looked at some rules of laws of limits, found out how to work with them and what they are, what they tell us. And then also looked at a few things regarding domain, looked at to be able to find some limits, and also then looked at some piecewise limits of piecewise functions. Thank you. Have a good day.